Good afternoon, everyone. So I'm going to talk about stochastic optimal control today. This is joint work with Professor Roy from India, who's also my ME supervisor. Stochastic optimal control finds applications in many different fields. For example, the control of vehicles, so maybe ground or aerial vehicles. It finds a lot of application in finance and also robotics. So these are just a few examples on the top of my head. And yeah, so let's start. This is what I plan to do. So I'll spend quite a bit of time on background, starting with the Feynman-Kac formula. This is a very famous and important result, which connects solutions of partial differential equations to those of stochastic differential equations. So we'll see how you can solve a certain type of PDE by just simulating some SDE and taking certain expectations. So that is the Feynman-Kac formula. Then I'll discuss what is the so-called nonlinear Feynman-Kac. And this too is also related to a PDE, which is slightly more general than the first case. So we'll see how you can still solve that by not just one SDE, but a couple of SDEs. So which is the forward-backward stochastic differential equation system. And these are sort of partly coupled or partly uncoupled system of differential equations. And then I will define the stochastic optimal control problem and also a PD associated with it. So that is the Hamilton-Jacobi-Bellman equation. And we'll see how the PDs of 2 and 3 are very closely related. And when certain conditions are satisfied, this PD related to 3 falls exactly in the category of 2, and you can use these methods, existing methods, to solve for that. And next, I will discuss an existing algorithm to solve an optimal control problem using this FBSDEs. And then I'll move on to the proposed method. So I'll discuss this in detail, starting with the derivation of the PD, then the derivation of the corresponding SDEs, and we'll see some examples, also some disadvantages of the FBSDEs and how we design SDEs that only move forward. And finally, I will discuss some numerical examples. So this work was actually targeted for a journal in mechanical sciences. So the applications are mostly on nonlinear chaotic mechanical oscillators. I will describe this when I get there. Okay. So let's start with an SDE. dxt is alpha dt plus sigma dbt. So it's a typical SDE. This first term is known as a drift, and the second term is a diffusion. dbt is actually this noise, which is a Brownian noise increment. And for any given SDE, you have an associated generator, which can be considered as the equivalent of a directional derivative if it was a deterministic function of a deterministic. So by Ito's formula, this is a very standard thing in stochastics. You can write the total derivative of a deterministic function of a random variable, like so. And this term, last term here, is and then I can write the function f by integrating this total derivative. And this expression in the box is an Ito integral, and it's a type of martingale. I will define briefly what a martingale is in just a minute, but this is a martingale. So if I take these two terms on to the other side, I have this expression inside the box, also a martingale. Okay. Right, so now let us take a function f such that it solves this PDE. So it's a backward PDE because it's subject to a terminal condition. So if I have such a function, then if I substitute this here, this would go to 0. So I have f is a martingale. And by the defining property of martingale, I have the conditional expectation of that martingale given information up to small time t is that function at t itself, the martingale value at t itself. So this doesn't have to be capital T, it can be any time which is greater than the small time t. But now, because I know what the terminal condition is, I substitute fxtt as g of xt, and this is what I have. Now also, because X is Markov, conditioning on the entire history is the same as conditioning on the latest information. And so this is what I have. fxt is expected value of g of x capital T, given xt takes, this random variable takes value x at time t. And this result is quite remarkable because you see the left-hand side is the solution of a deterministic PDE, it's a deterministic function. And the right-hand side, I have an expectation of a random variable. So this is how PDEs and a stochastic differential equation are connected. And okay, I'll discuss a more general case in just a minute. So now, instead of this right-hand side being 0, we go one step further and take this as a function which is r times f. So it's a linear function in f. And again, by the same Echos formula, I can write the total derivative. I substitute this from the PDE, and this becomes a special type of SDE. So df is rf dt plus another martingale. And this type of SDE, there exists an analytical solution, which is written here. And if I take this term, this exponential term, which is common to both these terms, onto the other side, next I will take expectation on this, and I have a more general form. So this is the Feynman-Kac formula. So again, I have the solution f to this PDE subject to a terminal condition, the same terminal condition, if I take this expectation of the random variable. So now, instead of just the value at capital T, I have the entire history of that random variable from small t up to the terminal time. Okay, where LT is the generator of the original SDE. Now we go one more step further and we say that this function, which was r times f, is now a more general function in f and del f del x. So it's semilinear because it's still linear in the highest derivative, which is inside this LT, the second derivative with respect to x. But I can have any function which may be nonlinear in x, t, f, and sigma transpose del f del x. So if I have this type of PDE, I can still solve this by simulating SDEs, but now I need to simulate a set of SDEs. So the set of dx and dy, these two SDEs, where the SDE for x moves forward and the SDE for y has to move backwards. I will discuss this in more detail when I talk about this in the context of optimal control. But the key difference between the Feynman-Kac and the nonlinear Feynman-Kac is in the former case, you had to just simulate SDEs forward. But in this more general PDE case, you need to have a set of SDEs. One of them has to come evolve backwards. Okay. Yeah, so now let's define the stochastic optimal control problem. I have a system given whose dynamics is given by this SDE. So again, same SDE. And the I should not have been a function of u, I'm sorry. So this is uncontrolled, it's not a function of u. And then I have a controlled system dynamics, which is linear in the control. So if u is the control force, then the dynamics responds linearly to this control. So that is where this linear comes from. And the objective now is to find a control history or the control trajectory ut such that this total cost is minimized. And this cost is quadratic in u. So that is what the quadratic refers to. Now this cost is split in two parts. The one is the terminal cost, which depends on the value of the random variable only at the final time. And the other is the running cost. Now, even the running cost is split in two parts. You have a running cost on X itself, and then you have a running cost on the control. So given that you start somewhere, this is the total cost. Now I will discuss the derivation of the AJB equation. This is probably the most boring part of the talk, but it's important. It's actually quite interesting. So instead of defining the total cost, I will now define the cost to go, a minimal cost to go, which is my C hat, such that the control of control U from small t up to the final time. So this is minimized. So I find an optimal trajectory U from t to capital T such that C hat is minimized. So the left-hand side is no longer a function of U. Okay, I just substitute the expression for this cost C hat from the previous slide. So this is terminal cost, a running cost. Now I can split this integral in two parts. One is from t to t plus dt, and the other from t plus dt to capital T. And I can push the minimum over t plus dt up to the final time inside, and that allows me to write a recursion in C. So Cxt, and this is Cx bar t plus dt, where x bar is the value that C takes at t plus dt. So now this is minimum over just instantaneous ut actually, given that xt is x. Okay. Next, what I need to do is I need to perform an Ito-Taylor expansion of this cost inside this cost conditioned on xt equals to x. So for an Ito-Taylor expansion, you need to do it up to first order in t and second order in x. So this is all pretty standard. So if I do that, then this is what, if I do that and I substitute this back here, then the C on both sides cancels, dt cancels, and this is what I am left with. So this is almost the HAB equation, the PDE for stochastic optimal control. But now since this expression is quadratic in U, I can actually find the exact minimum. So this is what we have. U star is the optimal control for a linear quadratic problem. And when I plug that back in, then this equation 2 is the final HAB equation. So this is a very compact form, del C del T plus this generator of C plus H tilde, where H tilde is this function, which is quadratic in del C del X. Okay, so now to solve the optimal control, this U star, I need del C del X. So for that, I need to first solve this PD in C. And if you notice, this PD is very similar to the one that I mentioned about nonlinear Feynman-Kac. So let's see. For the nonlinear Feynman-Kac, I wanted it to be a function of sigma transpose del F del X, but I have del C del X. So if you can somehow ensure that this condition holds, G can be decomposed as sigma times some kappa for some function kappa, then the equation 4, which is the HAB equation, falls exactly in the category of 3. And you can use the methods that exist to solve a nonlinear Feynman-Kac to solve the optimal control problem. Okay. Okay, so this is a slight digression. There are actually two ways to approach this problem. The first is to linearize the PDE. So if I do this transformation, C as minus tau log of phi, and subject to this condition on tau, then the PDE, the HAB equation, becomes a linear PDE, specifically a PDE of this type, backward Chapman-Congreve type PDE, and that can be solved by the Feynman-Kac formula. So although it's easier because you just have to simulate forward SDEs, the solution is restricted because of this constraint put on tau. So that's a trade-off. And the second way is to work directly with the HAB equation. So in this work, we follow the second approach. Okay, yeah. So this is now the forward-backward SDE method to solve the stochastic optimal control problem. This is my HAB equation. H is given by this expression. So in order to solve for this, I need to define versions of these two SDEs. So the version of X superscript xt is such that up till time t, it stays constant at the value x, and beyond that, it evolves as per this SDE. So in order to solve, I need to start at, in order to get Cxt, which is defined as y superscript xt at t, I start at x, integrate this SDE up till the final time, set y capital T by this terminal condition. So this y is actually C. It's just the convention. So y is nothing but the cost. So I set this yt as the terminal condition, and then I evolve this SDE for y backwards till I reach that same time t. And that will give me an estimate of the control at time t. So there's still a couple of points that I've left out, so I will try to explain it here. I really tried to write a pseudocode in LaTeX, but kept messing it up. So this is what I have. So let's start with by defining x, a version of x at small superscript xt as small x. Integrate this, so multiple trajectories. Because it's an SDE, it'll not be unique. So I have, say, m paths, and I have m values of x capital T. Then I set my y capital T as the terminal condition, g of xt. And then I have to go backwards all the way up to small t. But there is a small problem. So this SDE in y is a function of z, where z requires a derivative with respect to x of c. C is nothing but y. And you don't have y as a function of x, you only have it as a random variable. So in order to be able to do that, we perform an optimization or minimization at every time step, where I fit this y as a function of x at any time t. So yt is written as some basis function, is fit to a some basis function, and I find some alpha star so that I can write c in terms of those basis functions, and then I can write the derivative of c in terms of that, and that helps me find the control. Okay. Yeah. So there are certain disadvantages of using this approach. It's inefficient computationally, because at any time step, you have to go all the way forward and then all the way back in order to get an estimate of the control. And this integration duration is longest initially. And with SDEs, it's typical whenever you have an integration of an SDE, the errors accumulate with time because of the noise. So that's one major disadvantage. Another is you cannot apply this to real-time problems. And also the simulation of x and y cannot happen in parallel. Okay, so I now move on to the proposed method. We start by, so there are only two key differences. The first is we start by defining a cost to reach some x at time t, unlike the cost to go for AJB. And the second is I apply Ito's formula to this terminal cost x capital, so expanded about x0. So these are the two key points. Everything else just follows. And then what I get finally is a PDE in C star. And I also get a set of SDEs, which now only move forward. Okay, so again, this is the total cost. It's exactly the same. But earlier I defined it as a function of the lower time limit. Now I'm defining it as a function of the upper time limit. But the total cost in both the cases remains the same. I can write now this g of xt by an Ito's expansion, like so. So I've not written explicitly this Ito integral because we will be taking an expectation, and expectation of this would go up to 0. So I have now at some time t, the cost to reach some x given by this expression. So I call this entire function as a capital Q, which is a function of x and u and time, all three. Okay. So far it was a cost in terms, so as a function of u, so for any control trajectory, any random choice of control, this is the cost. Now I'm looking for the optimal cost, so which I minimize with respect to the control up to time t. And now, similar to the HAB case, I can write a recursion in C star. So this final expression is a recursion, but now t dash is less than t. So earlier I was going forward from t up to the final time, so that t dash was t plus dt. In this case, it is one step lower. So, okay, so this is just to give a very intuitive picture. This was the cost to go, so the shaded region orange, and plus this green spike, which is a g of x capital T. What I've done is I've actually smeared over this terminal cost over the entire time history. So this this green plot here. And I'm looking at the cost to reach at certain points. So 0 to t, but here it is the other way around. But the total cost in both the cases remains the same. So yeah, so that's the difference between C and C star. Okay, so now I follow the same procedure. I expand this, I do an e total expansion of C star about t again. So this is backwards, so this negative. And then similar to the previous case, I again have an expression which is quadratic in U, so I can find an optimal U star. And when I substitute that back into the PDE, this is what I have. So this is the final PDE in C star, which is the cost to reach at some x at time t. But this is now subject to an initial condition. So yeah, I think that's all I had to say here. Okay, and if I write the total derivative of C by Ito's formula, and then I use this PDE, then I get an SDE in Y, which moves forward. So this is these are two SDEs that have to be simulated simultaneously in order to solve for the optimal control. Okay. So it's a quick comparison between the HV equation and the proposed PDE. This was a PDE in cost to go with the terminal condition. And we now have a PDE in cost to reach with the same initial condition. And the C star is in some sense the opposite of C. It's not exactly the opposite, but in some sense, it goes in the opposite direction. And that is also visible in the sign of Q. So this Q was the running cost on X. Here it takes a negative sign. And there are also some extra terms because of this expansion of G of X capital T. Okay. Okay, so as I mentioned that we are mostly interested in controlling oscillators. The equation of motion of an oscillator is not a typical SDE, but is of this form, where I have acceleration term as well. So x double dot plus some function of displacement and velocity is sigma w. So this w here is white noise, which is v dot. And in order to deal with this, if x is n-dimensional, the system of equation is rewritten as a 2n-dimensional system. So right now I'm working with where x is 1D, but this would just readily generalize for any n. So for a one-dimensional problem, I now work with a 2D problem where the first equation is an OD. It's not really, it's a random OD. So it is dx1 by dt is x2. So x1 is displacement x, x2 is the velocity x dot. So you have something like x2 dot given by this equation. And if I put a control, that control would only act on the velocity. So this would be the controlled dynamics. And a generator for this type of system is given by this expression. That's the only difference. Everything else remains the same. So we have a cost to reach given by this same equation, except for the definition of the generator. And also now, since I'm considering a 1D case, U is 1D, so this is the total cost. Okay, and then this is the final PDE for the case of oscillators. In this is in compact form, the same thing, just substituting the definition of the generator. And the optimal control now is defined by the derivative only with respect to the second variable, x2. Okay. Yeah. And then we have the corresponding SDs for the oscillator system. This first is the SD for X, and the second is the SD for cost, subject to, again, the same initial condition, where the optimal control is defined by this expression. We again define Z as sigma grad with respect to X2. Okay. Okay, so this is a pseudocode for the proposed method. What we're interested in is the control trajectories of X and the control U, the entire history. And what is given is the system dynamics. So alpha and sigma related to the system dynamics. Q is the running cost on X. G is related to, it's a coefficient of the control in the control dynamics. R is related to the running cost on U. And kappa comes from the decomposability condition. So as to fit the AJB equation within the nonlinear Feynman-Kac. I think it may not be needed in this case because we don't really fit to the nonlinear Feynman-Kac, but I've still followed the same convention. G is the terminal condition, delta T is time step of integration, integrating the SDEs. And we also need some radial basis parameters for when we fit a function y as a function of x. Okay, so we initialize at x sum x0, and then y, z, and u are all functions of x0. We then integrate this for n number of time steps. For each time step, I need multiple trajectories of x and y. And in this case, because x at the next time step is already available, I can actually integrate y implicitly in x, even though it's explicit in y and z. So implicitly, I mean, if the time, I'm using k on the right-hand side, which typically would not be available. So you need better integration schemes to be able to do that. But in this setting, I already have it available, so I can use integrate y implicitly in x, where h is defined as by this expression. And once I do this for an ensemble of ensemble numbers x and y, I fit y as a function of x, then I can define z, and hence u. And this goes on for n time steps. Okay. So this is to compare the computational aspects between the forward-backward system of equations and the proposed method. So in the forward-backward system, because I have to go back and forth so many times, the total number of integration steps is much higher. So it becomes a series in 1 plus 2 up till n. So I have n squared plus n by 2 simulations of the forward dynamics of x, same number of backward dynamics for y, and then also the control dynamics for x. Whereas here, we don't explicitly need to do the uncontrolled dynamics integration. We directly have the control system, and we just go forward. So it's n in both x and y. And the next is this number of minimizations. So this is really the bottleneck of the entire algorithm in both the cases. And this requires these many number of n squared plus n type n squared order minimizations in the forward backward system, whereas here we need only n curve fittings. And because of this this longer duration of integration, that it's really the culprit. So it causes a higher sampling variance, a more computational time, and things like that. Whereas here, it will see in the results that it shows a much lower sampling variance, and it's robust as well. And in this forward-backward system, the x and y integration cannot happen in parallel. Whereas in this, on the other hand, if I chose to do an explicit integration x, I can actually integrate x and y in parallel. And we already saw this is not possible to do, not possible to apply a forward-backward system for real-time problems, whereas here it is possible to design some scheme. Okay, so I now move on to numerical examples. This first one is a very simple one-dimensional linear quadratic problem where you have the system dynamics given by this SDE, and this is the control dynamics actually. We start at the same point, I'm comparing 3 different approaches, start at the same point, and this is the total cost. So the running cost on x is actually 0, so it's just running cost on u plus the terminal cost on x. The first one is the forward-backward method. So I simulate this example some 50 times, and I get several trajectories. So even to simulate once, I will need an ensemble for the forward-backward system, but that would still give me 1 control trajectory. So I repeat that process some 50 times. And with this method, actually 7 out of 50 go outside this interval of -20 to 20. So I've not included that in the plot. But I see I forgot to put the correct results. So this is the total cost is with respect to all 50 actually. This is basically junk, so it doesn't really work. The next is a theoretical solution where the expression for u is available in closed form in terms of x as a function of x. So all you need to do is just simulate this SDE some 50 times. So this and yeah, just to remind, this is the total cost is what we are trying to minimize. So we have a total cost with mean of 4.3 and variance of 2.8, which goes very fast because it's just simulating an SDE. And then we have this third plot by the proposed method. So the total cost is slightly higher, but the variance is lower than even the theoretical. There's no magic. This is actually pretty standard. This is because of DBT. But because we have a system of two SDs here, the noises sort of cancel each other. And that is why you see a lower sampling variance even at a larger time step. Okay, so this was a 1D problem. Now we move on to a two-dimensional problem. I'm slowly increasing the difficulty level of these problems. This first equation is uncontrolled dynamics, and the second is the control dynamics. It looks like a linear system, but it actually behaves like an oscillator. So yeah, this was a transition between a simple linear problem and an oscillator problem. And these are the various parameters used. And the cost that I'm trying to minimize is this expression, which means that I want it to reach 0 and stay there for as long as possible. That is when the running cost and the terminal cost would be minimized. So we integrate over 0 to 10, and this is what we have. So I'm only comparing the controlled trajectories with the uncontrolled in this case. So what we set out to achieve, we're able to do that. Okay. Next, we have a Duffing oscillator. This is a chaotic oscillator. So in the phase plot, if you see displacement versus velocity, it doesn't really have any trend. It's chaos. And what we're trying to do is, again, get it to reach 0 and stay there for as long as possible. So again, the cost is designed so that x reaches and stays at 0. This is an equation of motion. There is a forcing term, cosine forcing term, and it has to be split into these two SDs as I showed earlier. I start with this initial condition. The thing with these type of oscillators is if I started at a different point, the behavior of the dynamics might have been much different. It could actually be a periodic plot in the phase space. But for this particular starting point, this is still chaotic, and we're able to control it to go to 0. And these are explicitly the displacement and velocity plots. So the thing with this is the velocity goes to 0 very quickly, and that is why the displacement is slower to go to 0. I actually tried to design the cost so that velocity wouldn't go to 0 that quickly, and that is the reason if you see the cost on velocity is lower than that on displacement, because they are two different types of entities. So it's possible to design a better cost so that they both reach 0 almost simultaneously. The results are better qualitatively. Okay. And then next we have the Duffing-Holmes oscillator. So this is actually a very important problem. Now, I only discovered yesterday. So there was an article which discusses control of only this oscillator. They study some 4 or 5 different methods of control to see what works best in this case. So for this example, this is again a chaotic system. If I start at different initial points, it might behave differently. And there are 3 fixed points. So fixed point is if you start there, you stay there, had there been no forcing. But this has a forcing term. So there are 3 fixed points. One is at -1, 0 in the phase space. The other is 1, 0. And the third is at 0, 0. So thus -1, 0 and 1, 0 are called stable fixed points because they sort of attract. But the 1 at 0, 0 is an unstable fixed point. So only if you were exactly at 0, 0, you would stay there, given that you made no integration errors whatsoever. But if you move away from 0 even a little bit, it will actually shoot off. So it will be chaos because it sort of repels. And these two attract. So hence unstable. Okay, and even for different epsilon values, the behavior of the dynamics would be different. But we consider a set of parameters where it's chaotic, and initial point also where it's chaotic. So in this example, I'm trying to control the chaos so that it's no longer chaotic, but it yields a one periodic orbit. So one periodic orbit is the oscillation of x matches with that of the forcing frequency. So the frequency of x and y matches with that. So I'll show that in the next plot. But this is what cost I use here. So it's like an ellipse at 1, 0 with a radius r. So I have some weight, x displacement minus 1 squared plus another weight. So this is like an ellipsoid. And this is what I wanted, and this is what I was able to get. So this is the phase plot, and we have explicitly then the displacement and velocity plots. So if you see this frequency matches with the forcing frequency of the system. Okay. This next is exactly the same problem, except for the initial condition. So I'm still trying to control the response of Duffingham's oscillator so that it stays in a one period orbit at this stable fixed point, 1, 0. But if the initial condition is far away from the strange attractor, what it's called, then it already is a periodic response. But what I'm trying to do is bring it to a smaller amplitude. So this is the phase plot, and this are the velocity and displacement plots for the same example. Finally, we have this is probably the most difficult case I've solved. I'm trying to control the same Duffingham's oscillator so that it stays at the unstable fixed point. So in this case, again, the cost is something like this, where the radius actually is 0. It doesn't really stay at 0 because of this forcing that is present in the dynamics. Had there been no forcing, it probably would have just stayed at 0. So this is the phase plot, and then we have the displacement and velocity plots for the same example. Yeah, I think I'm done with the numerical examples. So to summarize, we proposed a scheme to solve a stochastic optimal control problem that uses only forward SDEs, and we compare the results with the FBSDE method. So the results that I showed with this FBSDE, I don't think it's used directly the way I have used, because you always need something more, some sort of an iterative scheme or important sampling or machine learning. So I don't think it's used directly, and that's the reason that the results are junk. But we sort of built on that, so that's why I compared with that. Yeah, and we saw this is significantly faster and robust, and also exhibits much lower sampling variance. Okay, so yeah, so because the complicated part in dealing with the forward-backward system is backward SDE, so there are some articles where they apply some machine learning algorithm in order to solve the backward SDE. So you start at a random point and go all the way forward and find an error and then propagate the error backwards and things like that. So that's what is done. But even that is very inefficient computationally. And also something I didn't put in here is I derived the same method by going backwards, in the sense, instead of defining the cost to reach that I described, I actually tried to work with the cost to go, but with still the Ito expansion of the terminal cost. So I'm still smearing the terminal cost over the entire time history. But surprisingly, I get exactly, not at all surprising, I get exactly the same results. So I didn't put in here. It can get confusing. And then, okay, this third point I could have possibly put in the future directions, but it's possible to develop a forward scheme for the original AJB equation if you're somehow able to estimate the total optimal cost to go. This is not very straightforward because to get the total cost to go, you need the control solution. But because we are working in the stochastic setting, it may be possible to get an estimate with the deterministic control solution and do an iteration only initially so that you can just work with the forward SDs. Okay. Right, so finally, this actually can go in very many different directions. Something that I'm very interested in is its application to data assimilation. So I don't know how many people here work with, are familiar with the data assimilation framework, but you have, instead of one SDE, the system dynamics, you have another SDE, which is observation dynamics. And you also have some data, some observations. And the objective is to somehow find an optimal solution given both of these noisy things. So the system dynamics is noisy, the measurements are noisy. The objective of data assimilation is to minimize the noise somehow. And if people are familiar with the Kalman filtering framework, so that is actually a data assimilation method with an additive correction. That additive correction is actually nothing but change of measure. And whenever there's a change of measure, so it can be considered as a control. And so the filtering problem can be fit into the optimal control framework. And then you can just use existing methods from control to solve filtering. So there is some work on that where you use not just forward backward SDs, but you use a forward backward doubly stochastic differential equation. So this doubly stochastic comes because of the two noises, in one in the process dynamics and one in the measurement dynamics. So there is some work in that direction. And I'd be interested to work in that direction. And okay, so one specific example is the parameter estimation with control. So whenever you need whenever you need to estimate parameters of a system which you cannot measure or observe directly, this is often done in the DES setup, where you measure some function of that parameter and then try to infer it indirectly. So whenever parameter estimation is done in the DES setup, it's actually appended, the parameter dynamics is appended to the system dynamics. And since there is really no physics related to the parameter dynamics, it's just taken as noise, d theta as dbt. So I did some work recently where I put in a drift to that equation so as to direct it to the correct solution faster. And this can very well fit in with the optimal control setup. So I can define a cost which should be minimized so as to find a control on the dynamics of the parameter. I hope that made some sense. The next is to extend this approach using differential geometry. One case of this would be, suppose you didn't have a linear quadratic case, you had some more complicated function. So I did some work where I rewrite an SDE in Euclidean space to an SDE on a Riemann manifold. And so if it was possible to formulate the original control problem on the manifold such that even if it were not quadratic in the Euclidean space, maybe it behaves like a quadratic function on the manifold. And so we can use schemes that already exist to rewrite the control problem, a more complicated control problem in a simpler language if we were just able to use differential geometry appropriately. Another example is the application to variance reduction. So whenever you know where you'd like to reach finally, any problem where you know where you would like to reach, that can be posed as an optimal control problem. And with variance reduction, it is, you'd like to have zero sampling variance. So you know where you'd like to go. So that can also be posed as an optimal control problem. And actually, I think there is some work in this direction, but I'm yet to look into it. And finally, so there is this intricate web of concepts, very intricately entangled, vast fields of research in themselves. So one is this Dubs-H transform. I actually did some work for conditioning stochastic dynamic system using the Dubs-H transform. That can be posed also as an optimal control problem. Then there are concepts from non-equilibrium thermodynamics, like the free energy of a random variable or relative entropy of the random variable. These are all related things. So my knowledge is really puny on the subject, but I would really be interested to study these connections. It's very interesting. Okay, and that's it from me. There's a few key references. That's it. Thank you all very much for your attention.